Well, let's start. My name is Ritesh Harshe. I'll be talking about in this lecture about the Fourier analysis of gravitational wave detector data. I'll talk a little bit about dominant sources of noise and how we can learn about their properties using Fourier analysis. And towards the end, I'll also talk about how we can access the open gravitational wave detector data. So let's start with the outline of this lecture. So first I'll talk about gravitational wave detectors, uh, their structure as well, and their dominant sources of noise. I will also talk about how we can use Fourier analysis to learn about the noise sources. That will be done using fast Fourier transform. Then I'll talk also about power spectral density, which is actually kind of like a mean energy per frequency band. Then I'll talk about a process called whitening, uh, where you will see that you can convert a correlated data into an uncorrelated data. Spectrograms and Q transforms are alternative representations of time domain detector data. So I'll talk about those two things. We will discuss a little bit about glitches as well. And towards the end of this talk, I'll talk about this GWASC, GraceDB, and GWI-STAT, which are basically tools, web tools, which help you get the detector data and various other informations as well. So let's start. Gravitational waves are ripples in space-time produced by compact binaries which are accelerating and gravitating. The examples of such sources include binary black holes, binary neutron star black hole binaries, and supernovas as well. We have a worldwide detector network of these GW detectors, which operates to detect these GWs. We call it LIGO-Virgo-KAGRA collaboration. So you can see here there are 6 either operational or under construction detectors, and LIGO India is a planned one. Okay, all of these detectors are Michelson interferometers to their cores. And when you have loud enough GW, for example, when its signal to noise ratio, SNR for short, is larger than or equal to 8, you can call it a confident detection. Towards the end, we will see that this is a simplistic way of looking at it. The confident detection criteria is actually more stringent than this. Okay, so a model interferometer has a laser source, 4 mirrors like this one, this one, this one, and this one, a beam splitter, a photo detector, and 1 power recycling mirror. These 2 mirrors and these 2 mirrors pair together to form a Fabry-Perot cavity. Okay, so the laser source shoots laser at the beam splitter. The beam splitter sends half of the luminosity to this Fabry-Perot cavity and half of it to this Fabry-Perot cavity. This light bounces in this Fabry-Perot cavity for around 100 to thousands of times. And then it is sent back to the beam splitter. The beam splitter, at the beam splitter, it combines and it comes to the photodetector. Some of it goes to the power recycling mirror, which sends it back again into this Fabry-Perot cavity. At this okay, if the length of this and the length of this are same, and if the light in this the light coming from this Fabry-Perot cavity and this Fabry-Perot cavity are completely 180 degree out of phase, then you won't get any interference pattern here. But if the length of these 2 arms change, one arm is stretched and the other arm is squeezed, that produces interference pattern over here. Okay. Now there are reasons why this arm lengths squeeze and stretch basically change. One is because of the noise, and the other is because of a passing GW. Okay. So When there are seismic activities or bad weather or lightning, the ground vibrations can travel to these mirrors. And if these mirrors displace, you can get an interference pattern over here. But that is not because of GW. That is why it is counted. It counts as a noise. Another reason for noise is a Brownian thermal noise, where due to temperature and mechanical losses, the atoms in this mirror can do thermal fluctuation, can do thermal perturbations, and because of that, the length of these arms can change. Basically, because the mirror oscillates. So this is another kind of noise in the system. When, because the light in quantum regime can behave as a particle, which are called photons. These photons, when they strike these mirrors and come back, they transfer a bit of their momentum to these mirrors. And because of that, they set these mirrors into movement. And this is called radiation pressure noise. So that also gives you one kind of interference pattern over here. And then, because of this uncertainty of their arrival at the detector, you can have what is called short noise. This is basically the fluctuating stream in the photodetector. So these are the dominant noise sources that you can have. So this photodetector can detect these interference patterns due to this noise as well as a passing GW. So at the end, what you get is this, the strain, which is the change in the arm length, total arm length, divided by the total length. And that strain is a contribution of the noise and GW effects. Okay. So our detectors do measurements discretely. Like, for example, this strain that we are talking about, this is measured at discrete times, T1, T2, T3, up to Tn minus 1. This is a discrete measurement and it's not continuous. That we should know. Second thing is that the sampling of these measurements should happen at a sampling rate which is larger than 2 times the maximum frequency in the data. This is called Nyquist-Shannon sampling theorem. For example, if your sampling frequency is 32,768 hertz, that means that you are doing 32,768 measurements per second. So your sampling, the frequency of your measurements has to be larger than 2 times maximum frequency that you have in your data. That's how you will be able to reconstruct your underlying function, if there is one. Okay. So how do we get the frequency domain information of such a data? So this is time domain data, and we want to go to frequency domain to see various features in the data. So how do we do this? So usually when you have, in principle, infinite information about a function, you do what is called Fourier transform. You have to integrate from from minus infinity to plus infinity over the time domain, and that gives you the features in frequency space. However, what we have is a set of discrete measurements in time. So neither this is an infinite amount of knowledge, and nor this extends to minus infinity and plus infinity. So that's why you can't perform this Fourier transform here. You can't basically do this kind of stuff. So as a result, what you do is what is called discrete Fourier transform. So it is defined like this. These ones are your measurements. And this gives you the feature in the frequency space. So this algorithm converts the time domain data into frequency domain data, where the amplitude and phase tells you about the features of the noise. the inverse discrete Fourier transform is defined like this. And nothing special about this, but here is something special. When you put n equal to 0 here, and when you put small n equal to capital N here, two things. So this thing, when you put n equals to 0, it gives you this, and when you put n equal to capital N, this gives you that. So when you put this factor becomes 1. And in the case of n equals to 0, this factor also becomes 1. So at the end, what you get is S0 is equals to Sn times delta t. Now remember, we don't have this measurement. What we have are these measurements only, up to n minus 1. So what this is telling you is that the nth measurement should be same as the 0th measurement. What that is telling you is that implicitly the discrete Fourier transform is assuming that your data has to be periodic. It has to kind of like photograph itself again and again as you go in the future. So because of this kind of implicit assumption, you get spectral leakage. What happens is that the measurement at n minus 1 may not be that close to S at 0. And because of that, you get a kink if you do the inverse Fourier transform. And that kink is the cause of this spectral leakage. And what is spectral leakage? Spectral leakage is like not having discrete Fourier components in the Fourier domain, but it leaks in the neighborhood frequencies. Okay, so that is what is smearing, spectral leakage. So to solve that, what you do is you introduce something called window function. What it does is it kind of smoothly sets the data to 0 towards the end. So what it effectively does is it reduces the kink present at the boundary. Okay. Yeah. So there are different kinds of window functions: Hanning, Hamming, Tukey, and so on. Blackman that you can use. Okay. Okay, what is power spectral density? Power spectral density qualitatively tells you how much of an energy is in a particular bin given this data. Okay. Mathematically, how you can calculate it is if you have discrete number of samples in time domain and t is your period, total duration of your detection. Delta f is 1 over t, 1 over that time. And this averaging is done over multiple such data sets. And this is your familiar Fourier component at frequency f. So basically what you are doing is ensemble averaging over the Fourier component modulus square and then multiplying by delta f. And this gives you what is called power spectral density. If this n tilde that I am writing over here is actually noise only, then what you can also call it noise spectral density. The significance of this factor 1 by 2 is that it gives you this nice relation. The variation in the time domain, variance in the time domain, can be an integral over only positive frequencies, and this one-sided power spectral density. Okay. Okay, and you see, when you have noise over here, and qualitatively this gives you the mean energy in a particular bin. So what this tells you is that at that frequency, I have this much noise in the data. At this frequency, I have this much noise in the data. Okay, and you want to detect GWs instead of noise. You want to eliminate that noise. And these magnitudes tell you how sensitive is your detector at these particular frequencies. There are like spectrum of frequencies at which your detector will be characterized by this PSD, and it will also characterize the sensitivity of the detector at those frequencies. So this is also called as sensitivity curve. Okay. Then now that you know that power spectral density gives you the mean energy at each frequency, you have certain frequencies at which you have a lot of noise. You have certain frequencies at which you have a less amount of noise. If you have your strain data and you convert it in the frequency domain, what you can do is divide by what is called amplitude spectral density, which is square root of the power spectral density. What it will do is that relatively it will reduce the frequency component which has more noise, and it will relatively amplify the frequency component which has less noise. I hope this is clear. Okay, and when you convert it back into time domain, it basically has reduced the amount of noise fluctuations, and it has kind of amplified the non-noise features in your time domain data. Okay. Also, when your PSD has this bucket-like structure or any other kind of structure which is not flat, that is a signature that your noise in the time domain is correlated. The previous time step noise is the next time step noise is dependent on previous steps noise. So these are all correlations. And a flat PSD means that your future noise doesn't depend on your past noise. So there are no correlations. This kind of operation convert this kind of bucket-like structure to a flat PSD or a flat ASD. Okay. Now, why it is called whitening? Simply because something which has non-flat structure is called a colored noise. Something which has flat ASD or PSD, it's called white noise. Converting colored noise to white noise is called whitening. Okay. Okay, so now we are discussing about alternative representations of the time domain data. Spectrograms or later Q transforms, these are time frequency representations of the time domain data. They tell you the evolution of power in each frequency as a function of time. For example, over here, this color tells you kind of the normalized power in each frequency as a function of time. As you go like this, you will see the evolution of power. Okay. Yeah. The particular thing about spectrograms is that when you, okay, how do you calculate spectrograms first? So in order to calculate spectrograms, you have to calculate this called short time Fourier transforms. They are defined like this. So they are basically Fourier transforms only, but you at a given time, you take some amount of data about that time and you convert it into its Fourier components, and you basically lay it vertically here. So that gives you the spectrogram at this particular time. Then you do this exercise again and again for all times, you get this spectrogram. Okay. While you do this exercise, the amount of data that you take about this time is constant. What do I mean by that? Is that the time window you take about this time is kept same for all frequency components. So you see, when you calculate these frequency components, you have to get some amount of data. For example, over here, you have to take from 0 to n minus 1. So this is your whole range. In the same manner, here the delta t is your whole domain that you will use to calculate one frequency transform, and that will give you spectrogram at one time. In the case of Q transforms, your bucket in time domain that you use is a function of frequency. The number of time domain data that you use to, for example, get the frequency transform at this place is smaller than what you need at this place. So how does that help us? You see, if your frequencies are smaller, you basically have longer oscillations. For example, a 5 hertz signal can look like this, but a 51 will look like this. So at 5 hertz, you need a larger window to capture this kind of feature, but at 50 hertz, you need smaller time window. So that's how the Q transform solves this problem. Okay. So these are just those points. Then finally, let's talk about glitches. Glitches are like non-stationary, non-Gaussian noise, transients. They are either classified by their source or by their appearance in Q transforms. There are different kinds of glitches that you can encounter, and they appear quite often than you actually expect them to. So some of the names of the glitches are blip, whistle, fast slow scattering, coefficient, and there are more names over here. Yeah. Yeah. So when you have a random variable, if its statistical properties remain same as time evolves, that is called a stationary process or stationary random variable. When the statistical properties change, then it is called as a non-stationary process or a variable. Okay, and non-Gaussian means like in the Gaussian case, you sample from Gaussian distribution the random noise with certain mean and certain sigma. In the case of non-Gaussian case, its distribution is a different one. Because these glitches that you encounter in this one are actually non-Gaussian and non-stationary. Their sources could be like, for example, the power that you get in your time domain data due to electrical lines. Okay, it's not this thing. Okay, that's not good example. For example, a lightning bolt, lightning happened at a particular time. Okay, it will happen at that time, and then it won't happen again. Okay, for a little bit of, at least for some time. So what has happened is that it has changed the properties of statistical properties of your data for a bit of time, which won't come until some other, like it won't come regularly later. So such noise transients exist. That's why we have to care about them. Okay. 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 Now, actually, this is okay. I want participants to open this website, gwsc.org. If you have any question, please, you can ask. Okay, so if you have opened this website, mm, okay, you can see something called explore data over here. You can go there. You will see this window. This link tells you what kind of data you have, what cautions you need to take while handling that data. So please read this first, as it says. Okay. And then here, event portal, you will find all the confident, I think, confident detections we have done until now. This is not sure, but OSDF is a kind of mm, a grid of storage spaces which helps you download a large amount of data. Okay. And then here you can find the 4 kilohertz data of O4 observing run, 16 kilohertz data of the O4 observing run, its timeline, and then these are, I think, interesting things, auxiliary data. These are auxiliary channels, which are like seismic channels or kind of Newtonian noise channels, I think. And then you have, I'm not sure what this alternate strain is. Yeah, maybe other people can tell. Then you can open this GraceDB website also, gracedb.ligo.org. Okay. So the GWASC portal tells you the confident detections. GraceDB tells you the public alerts, which may be backtracked, which may not be actually like confident detections as well. So this S here stands for super event. It's also written over here, super events public O4. So if you go down in this list, you will find like this is probably very like confident detection with 99% probability. But there are certain public alerts which are for sure of terrestrial origin. You will find those public alert as you go down in this list. Okay, so we have seen that we can download the strain data of 4 kilohertz sampling frequency or 16 kilohertz sampling frequency. We have seen the confident confident detections. We have seen the public alerts, and then there is one site. It's this one. Okay, it's not here. Okay, okay, online.ligo.org. So this website tells you the current status of these detectors, whether it's like running, down, and so on, for how much time. Latency, I'm not sure what this is. Yeah. So any questions until now? Okay, and then we can conclude. We discussed brief working of the detector. Detector data is discrete and we use FFT to extract frequency content. PSD helps us characterize the sensitivity of the detectors. Whitening helps us dampening the noise dominated frequencies in the data. Spectrograms and Q transforms helps us visualize the data in time, frequency, space. Glitches can, okay, yeah. The main point is that glitches can mimic GW signals. That's why we also have to care about them. Okay, yeah, that I missed. And it is very important to mitigate them. And then we have seen these three tools, web tools, GWASC, GraceDB, and GWStat, that provide open data to us. Yeah, thank you. Slide of FFT. This. No. It comes out naturally over here. Put n equal to 0 here. And then n equal to capital N. What do you see? So n equal to 0, if you put, it's trivially this factor is 1. So you have only this thing. When you put small n equal to capital N over here, this factor cancels and k is an integer. 2 pi integer. So e to the I 2 pi integer is 1. So again, this is factor is 1. So you get again this thing. So these two are equal. Yeah, but we do know the systems, right? Gravitational wave systems, and what maximum frequencies they can attain. So we want at least that data to be present. Hmm. Yeah, I think so. Yeah. Yeah, that is there. But why don't we go above? Why the FS is not already the actual like hardware detect sampling frequency is 32,768 like hardware. Okay, photo detectors when they measure at this frequency. Okay. And why do we are already above that limit actually? Yeah. Yeah.
Eventually the noise will be so high, there is no point in recording. You will not see anything. That's why you just take some conservative.
I'm saying even we don't even have to go to these limits that we have for that. The strain probably ends at 1000. The systems we are interested in, their strain ends much before this. So we don't have to go to that high frequencies, but we do go. So yeah.
But as he said, it's a conservative estimate that in future when we upgrade it, we don't have to change the whole hardware for a different maximum sample. So it's a conservative estimate.
Okay.
In future, if LIGO attains those two,
The question was why we stop at that frequencies, or yeah, that's just the systems we are interested in. Any other question? Thank you.